All right. Hi. How's that? Hello, everyone. My name is Simon Rimmele, and this is my colleague, Deena Patel. We're from the New York City Mayor's Office of Data Analytics, and we're just going to walk through one of the projects we recently did where we relied a lot on Python around providing free school lunches to every student in New York City public schools. I'm just going to do a quick intro for anyone. Show of hands, has anyone heard of us before? Oh, there you go. Wow, okay. I'm flattered. Yeah, so we are a very small team of currently, are we 6? Yeah, we're 6 right now inside the mayor's office, and we act as, even though I hate to use the term, we're sort of like an internal data consulting function for the city, in that we are available for free to any city agency that has a problem or perhaps issues with using data or wants to use data more effectively, and that can span a wide range of different sort of applications, which is why we have this sort of rudimentary pyramid here about the way we think about data analytics, meaning we'd all like to spend our days fitting really cool models and doing some neural nets and whatever, but that's really the tip of the pyramid. And to get a city agency or team to the point where they're able to use those kind of things effectively, we have to start by managing their data and making sure that it's intelligible to human brains to begin with. And that really is the bulk of our work. So, the reason we have this pyramid is because it's wider at the base. We do more work at the base and we try to get to the top. So, that's maybe the frame of reference we do try to use for analytics. And I guess to segue into what we're actually going to be talking about, oftentimes we get work from the strangest places. The project Deena is going to talk about today came completely out of the blue when we met with the Department of Education's bus routing team. They were interested in routing buses more effectively, which is frankly a problem that I don't think the 6 of us are fully capable of handling right now. But there was someone else in the room who was in charge of the DOE's meal provision, so the way the department provides school lunches to every student in the city, and they had a very curious problem that they shared with us, and that's how this all got started. I'm going to turn it over to Deena now because she is the expert on the thing itself.
Thank you, everyone. Wow, this is a full room. This is exciting to have you all here. So we all know that there is actually no such thing as a free lunch. So who actually pays? We have the New York City Department of Education or any local school district, right? They're the ones who actually administer the program, and they're the ones who will actually apply to the federal government to get reimbursements. So this is what was brought to us. They said, look, there's this program out there, and it's a little bit different from the traditional way that we have been receiving lunch reimbursements. Can you help us with it? So traditionally, lunch reimbursements actually fall under the US Department of Agriculture, not the Education Department. So it's interesting right there, you see that this was actually a program meant to pay farmers for food, and as a secondary effect, you would feed kids. So it's just interesting to have that kind of background. And then, of course, the school kids themselves are the ones who also pay into the program, and they would traditionally pay at different levels. So depending on their family's income, so you would say, oh, this student, their family makes very little money. They don't have to pay anything, but we're going to get back most of that money from the USDA. But here's another kid whose family makes a little bit more, and so they'll have to pay a little bit more into the program, but and we're going to get a little bit less from the USDA for that kid. And then there'll be the kids who make just too much money, and they have to pay all of it themselves. So it's still it's still like maybe $3 a lunch, so not a huge amount, but for those kids, we only get a few cents back from the USDA. So already you're setting up this tiered systems where certain kids would get stigmatized. And because of this, advocates pushed for universal free lunches for all students. And as part of this, all students would have to receive the meals at no cost. All meals would be reimbursed by the federal government in the same way within a school. So one of these such programs that they came up with is called CEP. And there are multiple ones. I'm not an expert on these different programs. This is one that New York City is using currently. And this is a program that was started maybe a handful of years ago and has been in kind of a pilot phase. And so I think the last few years, New York City was using this on their middle school. So not all the schools, but just the middle school. This year, they were saying, oh, we want to expand it to all of the schools, which is why they actually wanted our help with it. So it's actually, this program is based on the percentage of what they call identified students in a school. And these identified students are ones whose families may be receiving food stamps or part of some other federal program that basically the Department of Education can match them back to one of these other programs. And so for some reason they call them identified students. So whatever the percentage is in that school, that's going to determine what kind of reimbursements they get. The trick to it, though, is it's not just the school itself, but schools can be grouped together. And so, and we'll walk through that a little bit. But essentially, there's really no constraint on how to group schools. And so, there's a lot of great kind of titles for this project. One of them is like free lunch for all, but another one is how we basically gerrymandered the school systems of New York City to get more federal reimbursements. And actually what we've come up with can be used for any local school district. It doesn't have to be, I'm sure New York City is probably the biggest school district in the U.S. with over 1 million students and over 1,500 schools. So this is already a huge problem, or just a quantitatively a big problem. And so, but the analytics question here is, what's the best way to group schools to maximize reimbursements in order to take full advantage of this federal program? The kind of spoiler here is that New York City actually they came to us this past summer to do this, and they said, oh, we're going to expand it. All the schools are going to be involved. How do we do this? In the end, there was some administrative change, and it turns out they were already at the maximum reimbursement that they could get, and they ended up not really needing our algorithm, so we put all this work into it, and they're like, oh, just kidding, we don't need it. But it's still, it was still an interesting project, and it's still something that I think other school districts could use because it is a federal program. So I'm just going to walk through now the reimbursement rules, the rules that we had to follow on this program. All lunches are going to be reimbursed at either the free rate or the paid rate. So imagine this is in one school, right? You can either be reimbursed here or here. And this threshold is where everything below the threshold, you're going to be reimbursed at the higher rate, and everything after at the lower rate. And the threshold actually depends on that percentage of identified students, and it's multiplied by this multiplier of 1.6, which is just a multiplier that they put in there. And the threshold, it has to be less than 100%. So you can imagine the threshold could go over 100% because you have this 1.6 multiplier, but it's capped at 100. And there's actually also a minimum value. So you can't be part of this program unless you meet the minimum. So this slide has a lot of equations on it, so just bear with me. And actually, I will also say that all of this stuff is on our GitHub account. So, and it's actually pretty well documented. We have an IPython notebook that walks through all of this stuff. So if you don't get it here, don't worry. This is just to give you like an overview. If you're interested more, please go and look at our GitHub. So the goal is just to maximize the reimbursements, which are basically the number of lunches times the price of the lunch multiplied by the threshold. And the same thing for the number of breakfasts, because this includes breakfasts and lunches for the kids. And the way I've kind of written out this equation, I've just put everyone is reimbursed at the base rate, no matter what. So I kind of just put that off to the side. That's just to make the optimization a little bit easier to look at. But that part doesn't depend on the groupings. So one thing you can do is you can think about, okay, how do we actually group schools? And what's going to be the difference if we group them versus not group them? So that's a delta R12, the difference between having them grouped. So R12 is when the schools are grouped together, and then the difference between that and just having them separate. So that's going to tell us if we have two schools, whether or not we should group them or not. Well, it turns out that if you do a little bit of algebra, you can come up with this equation, which is interesting because it's what's important there is a difference in the threshold. So threshold 2 minus threshold 1, that's an important part of it. And then the other important part is M1 minus M2. And I kind of call these M's. They're basically like the meal per student. And this is just the definition of them right here. But essentially the number of meals per student at that school. And N's are the number of students. So that final bit of it is actually I think it's like the harmonic mean of the number of students in the two schools, which is kind of less important. But so the interesting thing is that if the two thresholds are the same, it doesn't matter how you group them. You zero it out. So yeah, so you see the one where the thresholds are the same, R12, 0. Same thing if M1 and M2 are the same. You have this symmetry. So again, it doesn't matter. You can group them or you cannot group them. What does matter is when you have them off on a diagonal like this. Now it makes a lot more sense to group them. You're going to get a higher reimbursement from grouping them versus not. So that just gives you some kind of feeling into this is how we kind of first started looking at this problem, is try to take it in simple steps first and break it down and see, okay, can we do anything analytical with it? Okay, so this was my first idea when I got this problem, like, oh yeah, we can do this. We'll just do all the combinations. Of course, anyone who's done anything with things like the traveling salesman problem or problems like that, you know that that's not going to work. So, and luckily, when I was researching this, I saw, oh, there's this thing called the Stirling partition number, and this is the number of ways of grouping a set of objects. So the number of ways of grouping 3 objects into 2 groups is illustrated up here. We can count these on our fingers. It's 3. Great. As soon as we get to 30, the number of ways of grouping 30 things into 10 groups, now we're at 10 to the 23. Like there's even with just 30 schools, this method is going to fail. And of course, 100, doesn't work. But New York City has over 1,500 schools. There's no way we're going to get anywhere close to this by doing it this way. So we actually tried a number of different approaches, but the one that we found to be kind of the most elegant was Monte Carlo. And so this is based on the Metropolis Hastings Monte Carlo method, which maybe some of you are familiar with. And so it's really just 5 simple steps that you repeat over and over. The first step is you randomly group the schools into different groups. And you could do that, or you could just, I think what we ended up doing is putting everyone into one group to start with. So you could just initialize your problem somehow. And then you take a step. So in our case, a step was changing one school in a group and putting it into another group. So after that, then you compare the difference in reimbursements. If it was good, if it was better than what you had before, you keep it. If it wasn't, then you reject it and you start over. So you'll notice that this accept, reject, that number 4 step. So in like Metropolis Hastings, this is a really important step because it lets you figure out like your probability distributions, right? If you get the right detailed balance and all, this is a good way of simulating very complicated distributions. In our case, we didn't care about that. We're just trying to figure out what's the optimal reimbursement. So this method is also called stochastic hill climbing, which I think is such a great name for it because it's exactly what it is. You walk in a random direction. If you get higher on the mountain, you plant your foot there. If you don't, then you go back to your initial step. So I can't take credit for this picture. I actually stole it off someone else's talk, but I love it because what do we do about local maxima, right? So maybe we can't take any more steps. Maybe we started out over here, and we ended up at that one of the local maxima. We're just going to be stuck there. What do we do about that? So we tried another method called simulated annealing, which actually lets you take some backward steps. It's like, okay, it kind of relaxes that if your step is bad, it kind of still lets you take it some of the time. So the idea there is that maybe you'll hit a global maxima. So it's a very similar algorithm. The only difference is in your accept and reject. If delta R is greater than 0, you still always accept. But if it's less than 0, then you only accept with a probability of e raised to delta R over t. So t is like this made-up parameter, and it's essentially, it's modeled off physical systems where it'd be temperature. In this case, it doesn't really mean anything, except that we want to keep doing this, and at the same time, we let t go to 0. So this is essentially what the function looks like at different values of t. So you can see as you let t go to 0, you're again approximating that step function that was in the previous case, right? So essentially, as this goes to 0, we're getting back to the stochastic hill climbing. Okay, so I think I'm going to hand it over to Simon to tell us a little bit about how we kind of implemented this and made it run faster because we were doing a whole bunch of these at once.
I am going to pull up the actual code for this part. Yeah, we did write code, just so everyone knows. I think what's worth pointing out here is that when we did this originally, we just wrote code off the top of our heads, and we didn't really pay attention to efficiency, and it took a long time, on the order of 11 minutes to do this for, I think, 100 iterations. So then you want to do it over and over and over again to make sure that you're actually getting a good, stable solution. And it's not like we were writing, incredibly stupid, like 3 times nested for loops or anything. It just took a long time without using the pandas group by operator, which I think I've been using pandas for, I don't know, 3 or 4 years at this point, and it really took me a long time to figure out how to use it well. So I'm guessing everyone in the room is already totally comfortable with it. But I just want to I'd like to make a point of showing how it really helped save the day in terms of not having to run this thing overnight or on the weekend. And everything Deena's described so far, this reimbursement calculation is all right there. It's just one group by, and if you're new to pandas, I guess, or maybe you're coming from the world of SQL or something, you're used to a group by being an operation. Like you do a query, you get it back grouped, and you're comfortable with that. But what's really nifty about it in pandas, and you probably already know this, but for the sake of completeness, it's also an object. So here in this function, we're grouping by these arbitrary gerrymandered school groupings that we discussed. And you do it once, you can see it in the top line there. And from there, you can do whatever operations you want, however many times you want. In this case, we're just summing, we're doing different sums, but you can do whatever. And it is way faster to carry that thing around with you, group it once, and then do what you want, however many times before you group again. And to go back to the presentation, this is the difference it makes. So we go from 11 and a half minutes for 100 iterations to about a minute. And I know that won't impress any high frequency trading people, but it made a big difference for us. And if in the interest of time, it's all up on the GitHub. We'll share the link, and if you have any questions about that, I'm happy to talk afterwards. Now for the fun part, we're going to show a video. Yay. This is like the fun horse race video of it actually happening. And you can see how, unfortunately, we're not showing how schools move back and forth between groups, but you can see the optimal group slowly forming over time. And you can see we seeded it with 10 groups just randomly. Every school got placed in one of 10 groups. And running it over the course of, how many was this?
It took a few hours, I think.
Yeah. But you can see you get, and this happens in almost every time you run this, is you end up with what is one group with 100% threshold, so where everyone is reimbursed 100% of the time. And you end up with a middle group in the 85% range. And then a lot of schools end up, interestingly, but makes sense considering the math, they end up right above the 64% threshold. So they just squeak into the program by a hair. And you can kind of see that with the decimals. Some of those are 0.64 to the fifth decimal. And in order to counter for that, the ones we actually submitted, they had a little bit of padding built in so that if one kid leaves, this doesn't all fall apart. This is another way of looking at the same thing, sort of the different groups. This time in a scatter plot, with the two relevant variables, the meals per student on the y-axis and this reimbursement threshold on the x-axis. And sort of, I guess, in the vein of Dr. Gilman's talk earlier about showing workflow and methods, this is a comparison of the different things we tried. The most basic, obvious one is to make each school in its own group, which reimbursed about, I don't know, $180-ish million, looks like. Putting all the schools in one group isn't that bad. You get two, 225. Yeah. And then these other methods, we're not going to go into them, but they were deterministic greedy algorithms that we did the same thing but deterministically, and they would inevitably get stuck or have strange results that didn't lead to a good place. But the stochastic methods on the top performed better. What you can't see here is because of the scale, it's a little hard to tell how much difference it makes, but it makes about $10-11 million of difference in the total budget, which is on the order of 7-8% of the total school budget that you can just conjure out of thin air by doing this gerrymandering. And to just sort of put a bow around it, there is what happened this school year was, from the perspective of every kid in the school system, really great, which is that it just so happened that by a hair, there were enough eligible children registered in New York that this doesn't matter, that you can just put them all in one group and get full reimbursement. But it literally was by, I think, 3 decimal places. Like the threshold is 64%, and I think New York City as a whole this year had like 0.640008. So next year that might not be the case, in which case we can do this again, and then we can get close to the same amount of money. And if you're another reasonably large school district that has 10 or more schools, you can do this too. And it's all based on this USDA sort of regulatory arbitrage that we're doing. I'm not sure whether we should tell them, to be honest. But yeah, that's kind of the long and short of it. If you have any questions, one thing I should mention is we just recently published online on our GitHub pages this, along with several other projects we've done. So here's Free Lunch. There's also one we did on Legionnaire's disease back in 2015, and another for source of income discrimination. Each of them has a write-up, a abridged version of what we talked about here, and each of them has a GitHub with some notebooks or other code in it. So feel free to peruse at your leisure. And that's it for us, right? Any questions? Sure.
So, what was the penalty for using more groupings besides the obvious stochastic computational problems associated with that?
So the question was, what was the penalty to using more groupings? So why did we end up using this arbitrary 10? Yeah. And correct me if I'm wrong, but I think we were more or less told by the administrators of the program that we should aim for 10 or fewer because more would be both a gigantic administrative hurdle and might raise weird eyebrows. If we all of a sudden have like 37 groups that appear out of nowhere. So it was more or less just one of implementation. 10.
And just to add on to that, last year the DOE did this, and they had 10 schools, 10 different groupings that they actually just figured out through some spreadsheet manipulation type of thing. And the state and the federal government was like, no, that's too many. So we're like, okay, we'll just limit it to 10, which was fine because this problem is so unconstrained that it's extremely hard. So even limiting it to 10 was like not a bad thing for us anyway.
And you do end up with effectively 3 groups at the end, even though you start with 10.
Did you have how did you resist the urge to do like unstructured clustering? Like especially when you need to just drop schools into groups, the clustering tends to be really popular, especially in the data science set, and to use some unstructured methods would be like, oh yeah, this is great. Now we can identify cat faces, And so I really like the fact you have a very organized workflow here. And so I'm just curious, did you look at kind of using some of the unstructured methods, or was that not even in the framework?
I mean, I think there could be a lot of different approaches to this. I think I'm not quite sure what you mean by unstructured clustering, but
NMF jumps to mind, right? where you can select a K, and then you can take and allow the genes to kind of drop into natural buckets on their own.
Right. Well, I mean, just keeping in mind that we're trying to get at the maximum reimbursement was always our goal. So, I think different clustering methods would have different types of purposes. So we were trying to always kind of get to that goal. And like I said, I think sure there are a lot of different, we'd love to hear if anyone has some more ideas of what to do. I think it's definitely, I think another thing we considered was genetic algorithms, which you can kind of see this as almost a part of a genetic algorithm with only mutations. But you can imagine there are other ways of getting at it. In the end, this is like you're just trying to get the maximum. So, yeah.
The thing that I would add to that too is that I do see underneath this there is some clustering going on based on the rate that kids eat lunch at schools and the rate at which they are identified to get a free lunch is not random. There's demographic factors underlying that we just didn't use here at all. And I think another approach would have been to cluster based on those, and you would see different groups with different characteristics, and then you could maybe try to mash them together. But just to Deena's point again, I think given that we had the exact math in front of us, this was the quickest way to it. Mm-hmm.
The video where you're showing all the generation, please, pretty please, it would look really cool if you actually made those different colored dots on the actual geographic map, and you can see what the gerrymander looks like when it's all said and done. Please.
Yeah, I think we can do that.
Don't show the USDA.
Yeah.
So that was really great. I'm unclear what the three groups in the video are. Like, maybe you explained it, but it's not completely clear to me. Like, is anyone over the 65 getting food or free lunches, and then everyone above that also does? Or what are those? What is that number?
Yeah, so the 65% means that in those schools that were in that 65% threshold, 65% of the lunches were being reimbursed at the full rate, and the rest were being reimbursed at a lower rate. Whereas the cluster that was near 100%, it means every single one of those lunches was reimbursed at the full rate.
Okay, got it. Okay, great.
Yeah.
Thanks.
Yeah.
Hi, Bob Gunderson, USDA.
That's great.
Aside from the methods you showed, I'm curious if there's any like dream projects that you have that you'd love to do next, or if you had more resources. Like what's on the horizon?
Wow. Well, I mean, we work for city government. There's tons of projects. There's like tons of projects. I think our main focus is always trying to get the projects that have long-term impact within city government, and those that actually provide services to New Yorkers. So this was an example of, this is providing lunches to school kids and wanting that to be, universal across everyone. So these are the kinds of things that we really kind of look for. But I don't know. I don't know if I have any like off the top of my head.
I'm always a sucker for like sanitation and rats and stuff. I'm not quite sure what it would be, but that's kind of my domain.
Okay.
Thanks, everyone.
Thank you.